a question that's oftentimes asked is, will you need to know this to answer exam questions? So I might ask you, somebody puts their hands under a blanket and we put a spoon in the right hand and a toothbrush in the left hand, and then they're asked which it is, and various questions like that. All right, so which you need to know that the left hemisphere speaks, right? And that the right hand's connected to the left hemisphere, the left hand's connected to the right. You need to know those principles to answer all kind of questions that are similar. All right, so we're going to go into chapter 4 and the topic of sensation perception. So you can take in the upper division a course in physiological psychology and a lot of other topics. Of course, you can take a course in learning that we've had already, and abnormal psychology that we've had already, and we just finished up with biological psych. You can take courses in that, including the lab course I described. And there's a course in what's known as sensation and perception that you can take in the upper division. The current chair of our psych department is Eriko Stelf. Her specialty is in the field of vision, and so I'll mention a little bit about her work. So the idea of sensation and perception, we want to distinguish a little bit the idea of, or separate out sensation from perception. Here's one of the sensory systems. You can think about it this way: if you had no sensory apparatus, you wouldn't know anything about what's going on in the world. Because you got to be able to see or smell or hear or taste or touch something in order to know it's there. So there's a question philosophers have had is, if all your sensory systems were kaput, would you have any thoughts? What would your thoughts be? Could you have any thoughts? You can imagine not having some of these sensations. Well, here's a sense of smell, olfaction, and we need to distinguish the physics and the physiology, and that part of the study is usually called sensation. And usually what goes on up in this thought balloon is called perception. So here's the physical world. There's molecules coming off of this flower and going up into the nose, and they're being detected by specialized receptor cells that respond when the particular molecules touch them. The idea of the conversion from the physics of molecules touching neurons or touching these specialized receptors to a train of spikes is called transduction. So reception is the detection of the molecules. And then the spike events and the coding of spike events into the responses of the neurons is called transduction. And then these neurons are connected to other neurons up in the brain, and that's called coding. And then this coding is compared to something in memory. And this person comes to this conclusion. I drew this thought balloon in here to show us that we don't really think of that as being anywhere in the brain, but somehow epiphenomenal. So the person has a thought that there's flour here. And that thought, or that belief, that is called the perception. So the person believes there's a world there that created these sensations. Now the naive, you folks are walking around believing there's a world out there, that there's objects that you can touch, and there are things here. The only way you know about them is by seeing them, smelling them, tasting them, touching them, or feeling them. So that's the only way you have to know about them. And you have a theory that these objects are there. That theory of these objects is called a perception. You have a theory, this person has a theory there's a flower, and that explains the sensations that they had, which is how their body was able to detect something going on there. There's a little more detail from the olfactory system. Cut through the brain. Here's the cerebellum and the cerebrum, corpus callosum we were just talking about, the pons and the brain stem, the hypothalamus, which is connected to the pituitary gland. So when the hypothalamus detects certain hormones, it can trigger the pituitary to release other hormones into the body, or to stop releasing hormones into the body to repair bones, for example. Taking steroids might convince the hypothalamus, you got enough steroids, stop producing the ones that cause bones to grow. But we're focusing right now here on the olfactory bulb and the olfactory nerve and the detectors. So here are these specialized cells right here. They're specialized neurons that have dendrites that are designed to respond to chemicals that touch them. As you know, dendrites have postsynaptic membranes that respond to transmitter substances in the body. So usually they're tuned to be waiting for certain special chemicals. These are more generalized in that they'll respond to other chemicals that produce responses in these neurons. Here's some ganglion cells, and they're going to the brain doing that coding. So this is the system of olfaction. Here's an overview of the auditory system. So here's the outer ear and the ear canal and the eardrum. And the eardrum is connected to three little bones called the hammer, the anvil, and the stirrup. The stirrup is kind of convincing. It looks like a stirrup. You know, that was something that was invented in the Middle Ages that the knights could use to stay on their horse and not get knocked off so they could carry a lance. So it has that shape. Right. Basically, these three little bones, what they do is they amplify the sound. For you to hear something, what's the physics? There are vibrations in the air. So let's say a little something about the physics of sound here for a bit. Let me turn on the light. So we'll talk about making a little sound. Early instrument, a person has gotten themselves, they've eaten beef cattle, saved the skin, stretch out and dry out the skin and put it over a hoop. And so we've got a drum head here. Tightened skin that's been put out in the sun, taken off of a calf or a cow or something. Stretched out around the frame, and we've got a drum head there. And we could hit that, and it'll vibrate back and forth. And the vibration, when it goes this direction, it's going to compress the air. And when it goes back the other way, it's going to rarefy or make the air thinner. And this compression, if we had a whole lot of people lined up and I pushed the first one, and they were all touching each other, pushing the first one, that one would push the second one, and a wave would travel through the line of people, right? So if we had a bunch of people lined up chest to chest, I gave one a shove, they would each push the next one along. So the air molecules are compressed, and it pushes them all along, and that travels through, that compression travels through. So this thing is going to vibrate back and forth like pushing a kid on a swing. It's going to compress the air, and it's going to be places where the air is compressed and places where it's rarefied. And the whole thing is going to travel along. And it's going to travel at the speed of sound, which I mentioned to you before was about 700 miles an hour, maybe a little faster than that at sea level. So the air here is compressed, and here it's rarefied. If we look at the pressure level as a function of space and also as a function of time, so this whole thing is going to travel along compressions and rarefactions. So here the air is compressed, and here it's rarefied. So it's thinner and more compressed. And if we plot it as a function of space, we get compressed and, well, compressed and rarefied and compressed and rarefied and compressed and rarefied. And so these wave peaks are then going to travel along at the speed of sound. And the distance between the peaks is known as the wavelength. And if we wait here and we feel them coming by, we can count how many peaks come by per second. That's measured in hertz. As far as I know, not related to the car rental agency people. I don't know if that family's related, but related to another German scientist. And hertz are abbreviated Hz, and 1 hertz is equal to 1 cycle per second. And so wavelength, sometimes called lambda for wavelength, and frequency are inversely related. So the longer the wavelength, given that the whole thing goes at the same speed, the fewer cycles per second go by. All right? So this big thing goes boom, and it vibrates, let's say, 50 times a second. Back and forth, 50 times a second. That would be a low note. 50 cycles per second would be an extremely low note. The higher the frequency, the higher the pitch. If I had a smaller drum head and I hit it, it would make a higher sound, given the tension and the materials are the same. So the greater the tension, the higher the pitch. The larger the size, the lower the pitch is going to be. And so sound basically consists of compressions and rarefactions in the air. For you to hear something, there has to be air. If you're out in space, somebody blows up the Death Star, like at the end of the Star Wars movie. Folks know what the movie Star Wars, first of the series of movies. How many have seen the movie Star Wars? You know that the first story takes place in episode 4. That movie came out back in 1974, before you guys were even a gleam in your parents' eyes. 1974, they came out with episode 4 of Star. At the end of episode 4, what happens? You've seen the movies. They blow up the Death Star, right? And what does it do when it blows up at the end of the movie? It goes boom, right? But they're out in space. Would you hear a boom out in space? No, you wouldn't hear a boom out in space. Apollo 13, when it blew up, that's the unlucky Apollo mission that went to the moon, was going to go around the moon and come back. On the way out, they had a problem. Houston, we have a problem. You've seen the movie with, what's the name of that actor? Tom Hanks, yeah, thanks. Tom Hanks, is he the one who says Houston, we have a problem? Maybe they might have given him the line, maybe it was one of the other guys in the movie. Got the line, Houston, we have a problem. They heard the boom because they had air in there with them. But people on the outside, they would just see, that's just what you'd see if the thing, so you on the moon, if somebody yelled at you, would you hear it? No. Only if they have a radio and you've got one too to pick it up. Or if you had a string radio, then you could hear it. But you got to have some way of transmitting the vibration. So these vibrations in the air, they come along here. They vibrate the eardrum, which is fairly large compared to the opening on the cochlea, and vibrate that and press these bones, which amplify the message, onto the cochlea. Now the cochlea, we're going to unroll and look at down here in a second. There's another structure here, the vestibular organ, that consists of 3 tubes, each with detector hair cells, and they're at right angles to each other, so that you've got a way to tell your position in space. So this is the vestibular organ. There's a fluid in there. When you tip your head, the fluid moves over, tickles the hair cells, which allow you to know that you're tipped in space. Now there's a way to confuse your vestibular organ. Little kids learn this quickly. What do? They turn circles really fast. So if you turn circles really fast, or you sit down in one of those little toys where you control the thing and you can make yourself spin around like you see in at a kid's playground, kids will turn circles until all the hair cells have been so overstimulated, they're all firing like crazy. And then what happens? You get dizzy and fall over. In kids, it's not so dangerous as it is in old folks. They fall over, they break a bone, get a nosocomial infection in the hospital and die from it. Yeah, that's a very popular way to die in this country. For old folks, so we have to be careful. So that's the vestibular organ. Shooting off a gun or a firecracker near your ear can not only damage your hearing, but also damage the vestibular organ, and so the person may damage the vestibular organ can produce not only an inability to know whether you're right side up or upside down, or being, you know, how you're moving in space may affect your balance that way, but you may also get false signals, so that the person tends to throw themselves over simply because they're getting wrong information that they're tipped when they're not. So that's the vestibular organ. Here we've unrolled the cochlea, and there are hair cells all along the basilar membrane, and these hair cells are stimulating neurons. And you can think of this as like a piano keyboard with sympathetic vibrations. So, how many have played piano? I've ever had some piano. A few people have played piano. All right, so we got a piano here, and there's 3 pedals in the bottom of the piano. You can lift up the lid of a piano and look in there, and you'll see strings all different lengths. The longest strings are the lowest wavelengths. So if we have a long string, it's going to vibrate. If we pluck the string, it's going to go this way and this way. And at the same level of tension for the same type of material. Some of the strings are thicker and some of them are thinner. You can also adjust the tension to change the pitch. But for a given string and a given amount of tension, the longer it is, the lower the note it's going to make. So when you look in your piano, you'll see some long strings, those are the lower notes, and some short strings, those are the higher notes. And you can put your foot on that rightmost pedal. So we've lifted up the lid and we've got 3 pedals down there. That rightmost pedal, you will see it lifts up some wooden devices, each of which has a little, typically a felt tip that's touching the strings that stops them from ringing. All right. So when you play, for those of you who've had lessons, if you just play the note, it goes ding. But if you put your foot on the pedal and you play it, it goes ding, and it continues to ring until you lift up your foot, the pedals, and then they come back down again and stop it from ringing. So when you're playing a chord, you'll play like a piece. When the chord changes, you may move that pedal to stop the ringing of the other chord, start playing the next chord. So you put your foot down on the pedal, and now all of the little damps are lifted up, and all the strings are free to ring, and you can sing a note in there. La. And then listen back, and the piano is going to sing back. La. Same note you sang. Try a different note. La. La. So the piano will sing back to you by sympathetic vibration the same note that you sing in, if you sing one of the strings. Now this same string will vibrate in different ways, so it may also vibrate with a point like this. So this part of the string comes this way, this part of the string goes this way, and then this will flip back to this position. And so this same string may produce this note and also an octave higher. And so you may hear more than one, you may hear some more ringing when you sing a note in there come back, because you may stimulate more than one string, more than one note out of the piano. That's known as sympathetic vibration. The way to think about it is pushing a kid on a swing. If you are in sync with this kid, each time he comes back, you give him a push, and out he goes, and he comes back, and give him a push. The longer the rope that the kid is on, so he's hanging on a swing with a long rope, it takes longer for it to go, and if he's on a short little rope, then it's going faster, so it's a faster frequency. If it's on a long rope, he's going slower. And if I give him a push every time comes back to the same place, that's called a sympathetic vibration, right? Because it adds, and so the kid will go higher and higher each time. That's what's happening when I sing in there. These waves are coming along and pushing that string at just the right time. Each time when it comes back, the peaks are coming and giving it a push, just like me pushing that kid in sync. Now, if I push the kid at some other weird time, like he goes out and then I push him when he's just about to come back, that's unsympathetic, right? Boom. It's going to stop him with a sudden stop. So what's happening here is that these hair cells are tuned to different notes, just like those strings in the piano. And when you send a complex waveform in there composed of a lot of different notes, this cochlear membrane performs what's known in mathematics as a Fourier analysis, and it responds with the low frequencies and the high frequencies at different places along the cochlear membrane, just like the different notes of the piano that are laid out for you, from the long strings and the low notes to the short strings and the short notes. And it also will analyze it that way. Now, if you get damage to these bones in here, like you develop hardening of the joints, arthritis in the joints, or if an infection develops in here that damages the joints and not the cochlea, well, you could lose some hearing that could be restored with a hearing aid. So a hearing aid simply bypasses this amplifier and amplifies it for you. You can even drill a hole in and through the bone and create another like eardrum if the eardrum gets damaged. But if you get damage to the cochlea, that's called nerve deafness. That's the kind you do not want to get. Old rock and roll players warn you, don't expose yourself to loud noises. I play in a blues festival in Navasota, Texas. Some of these musicians that have been exposed to loud noise, they can't hear anymore. They have to turn up the speaker volume so high that other people can't even hear the notes. And the sound man, it was getting kind of sad. The sound man was a bass player, but he had turned up the bass so high, so many performances, that now he had the bass set up so high that people, you know, the bass was playing all kind of stuff, but all you were hearing was boom, 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 boom. You couldn't tell one note from another. He had the thing set up so high. So don't expose yourself to loud noises. Don't. That's why these people at the airport wear ear protectors. People that used to work in factories, they get nerve deafness, then they can't hear anymore. Now there's two kinds of deafness, just as there's two kinds of paralysis. You can have the hypotonic paralysis where you go limp, and you can have the spastic paralysis where the muscles are, as for example cerebral palsy, sometimes called the spastic, the muscles can't relax properly, and so the person has jerky motions. So that's another, so going limp is one kind of paralysis. Being tense and not being able to relax and coordinate your motions is another type of paralysis. In hearing loss, you can have a nice quiet kind of deafness, and that's the kind you would like to have. If you're going to be deaf, expose yourself to too much noise, want to be deaf, that would be a good kind of deafness to have. But unfortunately, the kind of deafness that too many people have is a noise deafness. So they're just hearing noise all the time. They can't go to sleep at night. They're hearing roaring sounds and squeaky noises and crickets chirping and water running and roaring. Can't turn the sound off and go to sleep. So they're just hearing noise. So that kind of tinnitus, that kind of damage that happens to the cochlear membrane. So if you're going to be in noisy environments, go to rock concerts where they set it up too loud. You want to wear some earplugs. You can bring earplugs to protect your hearing from that. Going to be working in a noisy factory, working around airplanes. You want to wear the recommended ear protectors. When I was a kid, we didn't worry about any of this kind of stuff. We used to just set off firecrackers, put our ears as close as we could to them to experience the ringing that happens afterwards as your cells die. They keep firing as they, screaming as they die, and you get to hear that. Your hearing goes back. All right, well that'll be it for today. We'll see you next time.